Good morning, everybody. This is Debasis Mitra, and I'm the host for today's seminar. It's part of the Sense Collect and Move Data Centers seminar series within the Data Science Institute, and also joined with the Electrical Engineering and Computer Science Networking Group. We are very happy to have as our speaker Jayakrishnan Nair, a professor at Indian Institute of Technology in Bombay. And his talk title is displayed there. It's about sizing and management of storage and smart power grid. I'll just say a few words about Jayakrishnan and something about the protocol for asking questions and handoff. Professor Nair received his PhD from Caltech in around 2012, I think.
Yes.
Yes, and I know that he spent a postdoc year at CWI in Amsterdam, right? And his research interests are in modeling, performance evaluation, and design issues in all involving applied probability, queuing theory, and also increasingly machine learning and so forth. Communication networks also. But he, together with his collaborator, Professor Ankur Kulkarni, who's actually also here, may have something to say. They have done some very nice, very interesting work on smart power grid. And that's what we're going to hear today. So, Jayakrishnan, it's all yours.
Thank you, Professor Mitra. Yes. Thank you for the introduction. So I'm going to be talking today about some of our recent work on sizing and management of storage in the smart power grid. Since I assume that the audience here might be from somewhat diverse backgrounds, I thought I'd start with some very high-level motivation for this brand of work in general. Yeah, so at a very high level, you can think of the power grid as basically consisting of three entities, let's say. There is generation, right? Then there is transmission and distribution. These could be different, there could be different entities that are operating in the space, but transmission and distribution's goal is to basically take the power that's generated by the generators and supply it to consumers like you and me, as well as industrial consumers, right? So there is generation, there's transmission distribution, and there is end users, customers, which might be both industrial or retail, right? Now, classically, the way the grid has been designed over the last century or so is in a manner that it operates with relatively modest supply side uncertainty and relatively modest demand side uncertainty, right? Why supply side uncertainty is small? Because for the most part, we have been using conventional generation, which, dirty as it might be, is extremely reliable, right? And very controllable. On the other hand, demand side uncertainty is also fairly small because over time, at moderate amounts of aggregation, right? You can actually predict within a few percentage points, what the demand in a particular location is going to be, for example, 24 hours in advance, right? Which allows the grid operator to basically match supply and demand somewhat easily, right? So we operate with small supply side uncertainty, small demand side uncertainty, and it is the former that is set to go for a toss as we introduce renewables at scale, right? So when you have a large scale of renewables into the picture, including solar and wind generation, you should expect that that's going to induce a considerable volume of supply side uncertainty. So this is just a picture here corresponding to the wind generation from a certain wind plant on different days of the month. So there are 30 curves in all, and you can see that things vary wildly, not just across days, but also within a particular day, right? So if that's the kind of generation which is going to power a considerable fraction of your overall electricity requirements, you can imagine that the manner in which the grid is operated and the kind of control algorithms that are required would have to be fundamentally different from what we are accustomed to over the past decades, right? So that's the high level motivation for us. So the big question in this space is, how is it that we are going to handle the supply side uncertainty that we will actually see a great deal of once we bring renewables into the picture at scale, right? And given our background, our approach to this, as has also been the approach of many other researchers, is to basically try and address various issues associated with this transition using tools from stochastic models, control, optimization, game theory, and so on, right? Using these bag of tools, you want to understand how to manage the uncertainty induced by renewables, right? So we've been working on this in this space for several years. So we have looked, for example, at how to procure conventional generation, right, which is controllable across multiple timescales in such a manner that you can most efficiently utilize the renewables that are present in your portfolio. We have looked at how it is that you should design operating points for the grid that are robust to short-term fluctuations induced by renewables, right? The short-term fluctuations should not, with high probability, result in, let's say, a line limit being violated or something like that, right? And in the last year or so, we have been working on this broad theme of sizing and management of battery storage with the intention of course, managing the uncertainty because of renewables, right? And this is this last piece of work that I'm going to be talking about in the present seminar, right? This is a joint work with my PhD student Vivek Deulkar, who is at IIT Bombay, and my colleague Ankur Kulkarni, who Professor Mitra mentioned a while back as well, right? So here is an outline of this talk. So I'm at a very high level going to be talking about the use of Markov modulated fluid queue models to reason about the sizing and management of storage in a power grid with considerable penetration of renewable generation, right? Think solar or wind generation. So broadly speaking, this talk will have three parts. So there are three distinct problems, related but distinct problems, that I'll be discussing. One of them is trying to address a very fundamental question that if I think of a bundle which is consisting of a renewable generator and a battery, how do I characterize the reliability of this bundle, right? So that's the first question that we will address. Then we will see that the same machinery that we use to answer the first question can in fact also be used to reason about the kind of economies of scale that are achievable if you're able to share the same battery between multiple renewable generators, right? They have to be far away. I put that in quotes and I'll make that precise going forward. But what are the kind of economies of scale you might get in terms of the volume of battery storage required if it is possible to share this resource among multiple renewable generators? And finally, we'll be talking about the sharing of energy now between two battery-equipped agents, which you can think of as microgrids, for example, right? So the first two of these, the first two problems here can be thought of as basically being relevant in the planning time scale, right? Because they deal with the issue of sizing of storage. The last, on the other hand, is relevant at the operations time scale because it is actually dealing with the scheduling of energy in a dynamic manner between two battery-equipped entities. Okay, so I will come to each of these in sequence. So let me begin first by talking about the first problem that I've mentioned here, which is the reliability of a bundle consisting of a renewable generator and a battery. Right. So this is the picture you should keep in mind, that I have a bundle consisting of these two things. Right. There is a renewable generator which essentially produces generation, according to that kind of cartoon that you see here, which is extremely variable, right? There is a battery resource that is part of this bundle, the goal of which is, of course, to smooth out the fluctuations that are inherent in the renewable generation. And the goal of this bundle is to basically deliver to a certain demand profile, right? This demand profile you can think of as, if the bundle be thought of as a renewable generator, which is, let's say, connected to the grid, that demand curve that you see is basically the curve of electricity or power, more precisely as a function of time, that the bundle is contracted to deliver in order to the grid, right? So this is the delivery curve, right, that it is trying to follow, that has been imposed upon it, right? So the question is, what is the reliability of this bundle? In other words, to what extent is this bundle capable of delivering to this particular demand curve? Okay? That's the first question we ask. And then you can flip that around and ask, if I give you a certain reliability threshold, how large a battery do you require in order to basically meet that level of reliability? Okay, so that's going to be the questions that we address. So So now let me get to the mathematical modeling of all of this. I mentioned this Markov modulated fluid Q. Let me describe that now. So what we have as part of this bundle is a generation process, which I'm calling G of t, function of time. We have a demand process D of t. Each of these is a stochastic process, right? And these two processes are basically modulating a battery of size capital B, right? And BT basically represents the amount of charge that is present in the battery at time t, right? So the amount of charge in the battery is basically varying depending on the evolution of the generation process and the demand process. Okay. So the simplest model here is that the rate of change of the charge level of the battery, remember B of t is energy, right? So the rate of change of that is going to be dictated by the difference between the instantaneous generation and demand. So when the generation exceeds demand, the battery gets charged. When the generation lags behind the demand, the battery gets discharged. And all of this is, of course, subject to the boundary conditions of the battery, right? Zero and the capacity, right? You can't charge a fully charged battery. You cannot discharge an empty battery, right? So this is the simplest model for battery evolution. And the crux of our Markov modulated model is as follows. So what we do is model this difference between generation and demand, right? The instantaneous generation and demand, we call it net generation, right? So it's positive when you have excess, it's negative when you run a deficit. So what we do is model this net generation process as some function of a background Markov chain, which I'm going to call as xt. Right? So there's some background Markov chain. That Markov chain captures all of those factors that might influence supply and demand, right? And the instantaneous net generation is modeled as some function of the instantaneous state of that background Markov chain xt, right? For tractability, we will assume that this Markov chain has a finite state space, arbitrarily large, but finite nonetheless. Irreducible, and for certain results we will also assume that this Markov chain is time reversible, right? It just makes some arguments just easier to make. Okay, so this is our model at a high level. What does this background Markov chain to be thought of as? We should think of this as some abstract Markov process, the state of which captures all of those factors that can influence supply and demand, right? So this might include, weather conditions. It might include the time of the day. It might include the time of the year. It might include the past values of generation that you've seen potentially in some window of time in the past. All of these things can basically be bundled together to form the state of this Markov process, which in turn determines the instantaneous value of net generation, right? So that's our mathematical model right there. So it can capture, if you think about it, it's a very general model. It can capture arbitrary dependencies between supply and demand. It can even capture battery ramp constraints, because that if you have limits on the rate at which the battery can be charged or discharged, that could just basically limit the values that this net generation process can take, right? So it's very general. I don't have to make any IID assumptions or anything of the sort. I can capture arbitrary dependencies with as rich a Markov model as the amount of data I have will let me build, right? So that's about the generality of the model. And mathematically, let me point out that this is actually an object that has been studied quite extensively in the queuing literature for several decades. In fact, this is in fact a finite buffer Markov modulated fluid queue, right? In the sense that there is the instantaneous drift of this buffer is dictated by the state of a certain background Markov chain, and it has a finite buffer, right? It's regulated on both sides, right? So this is an object that certainly mathematically has been studied for a while. Okay, so that's our mathematical model. Let me also tell you about what our reliability metrics are. So the reliability metrics that we will use is, the first is called the loss of load probability. So this is, so if you look at, I wrote this one out in detail so that I don't write the subsequent ones in the same level of detail. So the loss of load probability is basically the amount of time up to time t that you have experienced loss of load. What does that mean? That you have been unable to meet the demand process dt, right? The demand that was demanded at time t, right? So when would that be? If your battery is empty and at that instant, the generation actually was less than the demand. That is when you would not be able to meet the demand d of t. And the total time is basically what is captured by the integral up to time t. You divide that by t, that basically gives you the long run fraction of time that you have been unable to meet the demand, right? So the almost sure limit of that as t tends to infinity is what we call the loss of load probability. And another related, because the loss of load probability, if you think about it, only captures the fraction of time or the stationary probability of not being able to meet the demand, but it doesn't capture to what extent you're defaulted, right? So we also have the loss of load rate, basically, which captures the amount of unmet demand up to time t divided by t. And again, I take the limit as t tends to infinity. So this is, as the name suggests, the rate at which you are experiencing unfulfilled demand, if you will, right? So that's what we call the loss of load rate. These are our reliability metrics. So with this, I can now start talking about our results, right? So the first result is actually fairly trivial. I'm just stating it here to get it out of the way. If your stationary net average net generation were negative, what that means is that in the long run, your time average generation is less than your time average demand, so which means you're generating less than what needs to be supplied, then it's clear that no matter how large a battery you choose, you're not going to be able to meet an arbitrarily tight reliability threshold, right? So that's just stated by this lemma that if your net generation were negative, average net generation were negative, then no matter what your battery size, there is a positive lower bound on your loss of load probability, right? Because you're just not generating enough. So the real interesting question, if you care about reliability, is the case where your average net generation is in fact positive, right? So, so the main theorem is here. It says that if the average net generation is in fact positive, then let me just state what this expression means, and then I'll parse it. So if you take the logarithm of the LOLP and the LOLR, the logarithms of these two quantities decay linearly, which is being captured by saying that if you take the log of the LOLP, divide by the size of the battery, if you then stretch the battery size off to infinity, you get a certain constant, right? That constant is called lambda, right? And the same is also true of the loss of load rate, right? And this constant lambda, which we will interpret it as a decay rate in just a bit, can in fact be characterized a bunch of ways. It can be characterized either in terms of a certain large deviations rate function, or it can be characterized as the eigenvalue of a certain matrix, right? A particular eigenvalue of a particular matrix that is dictated by the Markov modulated fluent cube parameters, right? So I'm not going to get into the details of the characterization itself. I would refer you to the paper for those details. But the point here is that you should really interpret, that what that mathematical statement above really means is that both the loss of load probability and the loss of load rate decay exponentially with the size of the battery, right? And the decay rate, if you will, the rate of exponential decay of each of these quantities is precisely this constant lambda, which can be characterized, right? In terms of, as I said, either you can have an eigenvalue characterization of this, or one can characterize this, one can compute this, in fact, explicitly in terms of a certain rate function, a large deviations rate function. Okay, so the moral of this theorem is that if you're, so long as your net generation is positive, right, the reliability, which is captured either by the loss of load probability or the loss of load rate, decays exponentially with the battery size, which is another way of saying that no matter how tight a threshold you might have on reliability, it can actually be achieved by having a large enough battery. So if your buffer is large enough, you can actually meet arbitrarily tight thresholds of reliability, right? So that's the main takeaway here. This is not, I should point out, a particularly surprising result. In fact, if you take away the fact that there is actually regulation on both sides, if you only account for regulation of the battery on one side, which is currently the equivalent of saying that you have only one boundary to the battery. This is in fact a statement that goes back a good 30 years to a paper by Professor Mitra. The only technicality here, which I think is not particularly difficult, we just didn't find this precise statement in the literature elsewhere, is that we have to account for the regulation on both sides, right? And that adds one layer of technicality and some results from large deviations in order to basically justify this, right? That's all. So the main point here for us was to basically apply this to actually do battery sizing in practice, right? So, so that there is the approximation that is suggested by our theorem, that the loss of load probability can be roughly thought of as basically being some constant into e raised to minus lambda b, right? Where both the decay rate lambda and that prefactor c are essentially dictated by the model, the Markovian model that we have constructed, right? both of these can be in fact computed using that model, right? A trivial consequence of this is that if your battery is large enough, you should expect that increasing your battery by 1 unit of size is going to shrink your loss of load probability by a factor of e raised to minus lambda. So that basically lets you do some basic relative sizing exercises, but you can also do absolute sizing, it turns out. Right, so suppose that your target for the LOLP is epsilon, where epsilon is 10 raised to minus 1, 10 raised to minus 2, whatever, 10 raised to minus 3, some reliability level that you might seek. Then just by inverting that approximation formula up there, you will see that the required battery size for that is going to be dictated by, well, log of your prefactor by lambda plus log 1 by epsilon divided by lambda, which again, if your epsilon is sufficiently small, you should expect the second of these two terms to dominate, because log of 1 by epsilon will become much larger than the log of your prefactor. And so your second order approximation would just be to take the battery size approximation to be log of 1 by epsilon divided by the decay rate lambda, right, which has been characterized in the theorem before, right? So we have actually done some extensive work in fitting Markov models to real world traces of renewable generation, computing these parameters and seeing that in fact the kind of sizing estimates one gets from these asymptotic approximations are in fact fairly accurate in practice, right? So I won't go into the details of those numerics given the space, given the given the time constraint, but I'm just going to refer you to our paper for the details there, right? So I won't go into the details of the numerics, but I'll just mention one number so that we have some sense of the scale involved here. Consider that you have just a single wind turbine, right? It's in some location of the US. The precise location is irrelevant here. And suppose that the nameplate capacity, which is the peak generation of this wind turbine, is 16 megawatts, right? And given the trace of this that we had for 5 years, the empirical average of the generation that's actually obtained from this wind turbine is about 6.5 megawatts, right? So you can see that what you actually get is only a small fraction of your nameplate capacity, right? Now, what we do is basically use that as my G of T, my generation process. And I set the demand as basically going to be, for simplicity, just a constant at 60% of the average generation. In other words, 60% of 6.35 megawatts, right? And the question now is that in this case, how large a battery do I require in order to, with, let's say, with a reliability of 90%, which means an LOLP target of 10%, be able to meet this constant demand, which is 60% of my average generation, right? So it turns out that the size of the battery you need here is approximately 100 megawatt hours, right? I mean, that's a very, very, very large battery size. It's comparable. It's probably one order of magnitude less than perhaps the largest utility scale battery installations that I'm aware of. So the point I'm trying to make here is that the inherent uncertainty of this process, the inherent intermittency of this process is enormous, right? So it takes, even if you are willing to give up 40% of your average generation and say, I only want to meet 60% of the average generation, but steadily across time, I need a ginormous battery to be able to carry out that kind of smoothing, right? And this battery is large enough to be able to just supply the demand process by itself for more than a day, right? So that gives you a sense of the scale of variability that is inherent in these sources, right? So a natural question you should then ask is, I mean, what do we do about making these battery requirements manageable, right? Because this is clearly not going to be sustainable. This is just one turbine, right? So you can imagine the kind of storage requirements you would have if locally you had to basically meet the reliability requirements of each of these generators, right? So a natural answer that presents itself is that to make the battery requirements manageable, you should exploit the inherent statistical economies of scale, right? By that, I mean that you don't want to necessarily smooth out the intermittency of a single source right there, but hopefully you want to smooth out the intermittency of one source using another source, right? So that the instantaneous excess of one source can make up for the instantaneous deficit of another, right? Such that the overall battery requirements might be somewhat more manageable, right? So that actually is a segue to the second part of this talk, where I'm going to be talking about using the same model that I built up so far to talk about economies of scale that are achievable from sharing of storage between, what is currently quotes, in quotes, far away renewable generators. So since I'm done with problem 1, if there are any questions at this point, I'd be happy to take them, or else I can continue forward and take questions in the end.
No one seems to have raised their hand. So, Jayakrishnan, I think.
Maybe I'll just go ahead. Yeah. Thank you. Yes. Okay. So I'm now moving on to
Jayakrishnan, maybe I'll just add one little comment here before you. So the one sort of intuition for why the battery size ends up being so large could be that the nature of wind itself. That you have wind when it blows for several contiguous periods, but when it does not blow for a several contiguous periods. So in sort of it seems like in the long run, what you need is a battery that will provide you enough reliability for all the lull periods that you're going to encounter. That seems to be roughly what this result seems to suggest.
Okay, thanks. Okay, so let me move on now to problem 2, which is on economies of scale coming from the sharing of storage. Okay, so I'm going to use the same mathematical model as before, except that instead of one bundle, I will have n such bundles, right? So n such bundles consisting of renewable generators and batteries, right? Each of them, of course, let us, for the sake of argument, which are supposed to meet a certain reliability requirement of epsilon, right? So each of them has their own demand process, and so they have to set up their battery. They have to meet the demand up to an LOLP threshold of epsilon, all right? And so the question we want to ask is that how does this scenario, this baseline scenario, compare against an alternative scenario where these n bundles in fact share their battery, right? So instead of having their own, shall we say, individual battery, they have like a shared battery resource which is leveraged by all of these n resources, right? So it's simultaneously charged and discharged by the sum total of all of these n sources. How would these two scenarios compare, right? In particular, the question to be asked here is the shared battery size BS that is required in order to meet the reliability threshold for each and every one of these n sources, is it significantly smaller than the sum total of the batteries that you would require if these sources were to meet their own, smooth out their own reliability kind of in a standalone fashion, right? So that's basically what I mean by economies of scale. And before I go further, let me just point out that the picture on the right is essentially just a logical representation, right? I'm not suggesting that this shared battery be one physical resource. It could be multiple resources fragmented and strategically separated. It is just that they are operating as one in that they jointly serve the n renewable generators together. That's what I mean by representing it by a single battery of size BS, right? So the question is there a lot to be gained from this? Is BS significantly smaller than summation BI, right? Let me remind you that we just came up with this, large deviations based approximate characterization of each of these battery sizes. So each battery size is basically just going to be log of 1 by epsilon divided by the appropriate large deviations decay rate associated with, the asymptotics associated with the size of the battery going up to infinity, right? The appropriate lambda, if you will. So our main result here is the following, that if the n net generation processes corresponding to each of these locations, if these were mutually independent, then in fact, the lambda, the decay rate associated with the shared system is going to be greater than or equal to the smallest of the decay rates of the standalone systems, right? So lambda is going to be at least as large as the smallest of the standalone decay rates, if you will, right? If you combine that with the approximation for the battery size that I've just outlined before, you will see that what this means really is that the shared battery size that you need in order to meet this reliability threshold for everybody at level epsilon is at most the max of the battery size of each of the individual resources standalone, right? So this is, you can imagine that's a tremendous saving, right? Because the largest of the batteries that you had on the left, just one of them is sufficient to jointly meet the reliability requirements of all of your n sources, right? So you can imagine that, this is basically saying that the shared battery size is essentially order 1, right? You can scale the number of renewable generators off to infinity, but with n sources, you might think that the battery will scale, sublinearly, right? Because of economies of scale. Because if these renewable resources were perfectly correlated, it's actually a straightforward exercise to see that your shared battery size would in fact grow linearly with n, right? So economies of scale, you might think, corresponds to some sublinear growth at n, right? Maybe square root n if your central limit theorem intuition serves you right, but it's actually order 1. The shared battery size, in fact, is scale invariant. It doesn't scale with the number of sources, right? So that's a tremendous saving to be had, an n-fold saving with n sources, right? Roughly speaking. So that's what is achieved. You get tremendous economies of scale. However, this is a mathematical result which relies on this mathematical idealization called statistical independence, right? Which of course is not going to hold in practice. So the question is, can these economies still be observed in practice? Right? So we did some experiments again by collecting generation data across a bunch of locations, and so we actually sourced this data out of the National Renewable Energy Laboratory, NREL. Each of these generators, as before, has a nameplate capacity of 16 megawatts, and the demand process, exactly like before, is taken to be 60% of the average generation and constant across time, right? And so here is what we do. We basically have a large trace, and so we simply simulate this for various battery sizes and see how large does your battery size need to be, shared battery size need to be, in order to meet a particular reliability threshold, which I believe is, I'll show you results for a bunch of different reliability thresholds, right? So here is my first example. So we have chosen 4 locations, which are approximately, 125 miles or 200 kilometers apart, right? And what we are plotting on the right is basically the shared battery size as a function of the number of sources that are actually coming together, right, to share, right? And you see that, when sources are as close as, 200 kilometers or 100 odd miles, the economy of scale is actually fairly modest, because you see that the shared battery size roughly grows linearly with the number of sources, right? Which is to be expected, because the wind that is actually generated at these 4 locations is very, very strongly interdependent, right? Very positively correlated, if you will. So you should expect that you would have very modest economies of scale, if anything at all, if your sources are in fact as close as this. So next, we stretched the sources a little further apart. Now they are, I put this in miles, 125 to 300 miles, which roughly corresponds to 200 to 500 kilometers. Okay. When you do this, you start seeing some flattening. That is, the shared battery size is not growing linearly, but very noticeably sublinearly with the number of sources. Right? We have done experiments with many more sources also. I'm just presenting these because they're easy to read. Right? So you see that there is a significant flattening, but it's not quite. It grows sublinearly, but it's not quite insensitive the way our idealization, assuming independence, would suggest. Then we stretch this. Yeah, you get modest economies of scale. You can also see that the economies of scale are more pronounced when your reliability thresholds are loose, right? And we conjecture this has something to do with the fact that rare events, when it comes to meteorological conditions, are perhaps more strongly correlated than non-rare events, right? Which is why you see the flattening happen a lot better when your epsilon is larger, which means that your loss of load probability is not dictated by that rare, and if that rare a set of events, and so those are perhaps more quote unquote independent, right? And then finally we stretch these locations even further apart, approximately 500 kilometers or upwards of 300 miles, and then you see that the shared battery size in fact is essentially flat, and in the case of the lower reliability thresholds, actually seems to be even decreasing with respect to the number of sources, right? So you see that in fact the kind of economies of scale that the theory suggests under the idealization of statistical independence are in fact also realized in practice, with a geographical separation of approximately upwards of 300 miles, right? So that's the kind of separation over which one needs to share energy and share storage resources in order to achieve the kind of economies of scale one would get had one had statistical independence, right? So this is the kind of shall we say manner in which geographical separation can act as some sort of a proxy for statistical independence. Right? This is the amount of geographical independence one requires, right? So to conclude, from essentially the last two parts that I just presented, we talked about this Markov modulated fluid queue model for characterizing the reliability of a bundle consisting of renewable generation and battery. We exploited the same machinery to talk about the economies of scale that are attainable by sharing this battery between multiple renewable generators. And we saw that, in fact, there are tremendous savings to be had, an n-fold reduction, if you will, among n participating generators, right? And we actually do a case study. You can see a lot more extensive coverage of this in our paper if you're interested, which again shows that these savings are in fact actually achievable in practice, right? So that actually brings me to the conclusion of the first two parts of the talk. Yeah, let me just mention this quickly then. One thing that our mathematical model, as I outlined so far, does not capture is loss, right? I kind of, in writing that ODE as simply, the rate of change of battery charge level is just the instantaneous net generation. In writing that, I implicitly assume that the battery is ideal, right? It doesn't leak energy and so on. But that's a natural and very important practical consideration to take care of. So it turns out that the same broad machinery can also be actually applied to account for battery inefficiency. This boils down to basically applying an additional drift term to your battery evolution, which depends on the instantaneous battery level, right? Interestingly, mathematically, this is in fact equivalent to another piece of work that was done by Professor Mitra, I think back in the 90s, on a fluid analysis of this networking, shall we say, algorithm called RED, or random early dropping, right? So you have a buffer. This is only for those of you who have some networking background, where you kind of drop packets ahead of time before the buffer becomes full. As a result of which, if you study a fluid model of that buffer, you end up with a scenario where the drift of the buffer depends on the level of the buffer, right? Which mathematically is exactly what one would require in order to capture loss, right? So this framework, in fact, allows you to do that. This framework also allows you to think about demand response, right? Because you can think of demand response as basically a curtailment of demand that is done when you are about to run low, right? If your battery level dips below a certain threshold, you start curtailing demand actively, therefore changing the drift levels and so on, right? So therefore this modeling framework also allows you to capture demand response. It also motivates a couple of economic questions. Like, for example, in order to actually allow for the dynamic energy transfer that is involved in sharing a battery between multiple sources, potentially several hundred miles apart, you need the transmission capacity to be able to support that kind of dynamic energy transfer, right? So the question is, how should one, in fact, augment transmission capacity to be able to achieve and realize these economies of scale in practice? That's an important economic question. Another question is, of course, on what are the market regulatory interventions that are required to basically enable these kind of long distance dynamic energy transfers between regions of surplus to regions of instantaneous deficit, so that the overall requirement of storage in the system comes down drastically. Right? So these are two natural economic questions that are motivated by our work as well. Okay, so at this point, I'm done with part 2 of 3 of the talk. I can pause for a second to see if there are questions. If not, I'm happy to continue.
I don't see any hands raised, Jayakrishnan.
Thank you. Okay, so let me now move on to the third piece of work that I wanted to discuss, which is on the dynamic sharing of energy between two battery-equipped microgrids. Right? So the motivation for this is slightly different, even though the mathematical formulation will actually be, as you will see, quite similar. So the high-level motivation for this third problem, as I said, this something that is relevant to the operational timescale, is as follows, right? Consider you have two agents. I'm calling them agents for a reason, as it becomes clear in a bit. So you have two agents, agent 1 and agent 2. Each of these agents is associated with their own stochastic generation, their stochastic demand, and a battery, right? So each agent is equipped with this. And so what would examples of agents be? These two agents, for example, could each be remote microgrids, where these microgrids have their own local renewable generation, they have their own local storage, and they meet their own local demand, right? Alternatively, you can think of these agents as being grid-connected renewable generators, like the kind that we have been discussing in the previous parts, where I have a certain, let's say, wind farm, and I have a co-located battery, and I am basically contractually obliged to supply electricity to the grid according to a certain time profile, right? So that therefore completes the three pieces to define that entity. Alternatively, these agents could just be grid-connected prosumers, right? People like you and me, for example, who have rooftop solar and we sell electricity to the grid, or potentially we can share it with one another, right? So you have these two agents, and the reason I use the word agents is because they are strategic entities, right? So they care about their own local reliability. And so what is the goal of each agent? The goal of each agent is to meet its demand as reliably as it can, right? Specifically, the goal of each agent is to minimize its own loss of load. Okay. And so the high level, shall we say, motivation for this third piece of work is, can we think of dynamic energy sharing between these two agents in a manner that actually increases the reliability of both? In other words, in a manner that is mutually beneficial to both agents, right? So what is the intuition here? It could be that one agent is facing a deficit, but the other agent has energy in its battery, right? So the other agent could actually transfer energy back to the agent that's facing a deficit in return for a reciprocal treatment when when it is the supplying agent that actually runs a deficit, right? So they could help each other in times of need, so to speak, in a manner that is actually mutually beneficial, right? So that's the high level motivation for us. And our main contribution is that we show that one can come up with a very simple dynamic energy sharing mechanism, which is in fact guaranteed to basically induce mutually beneficial sharing configurations. More precisely, we propose a sharing mechanism such that there is guaranteed to exist a mutually beneficial sharing configuration. This is true irrespective of how asymmetric these two agents might be, right? For example, one agent may be a lot more deficit prone than the other. One agent may have solar, the other may have wind. Nonetheless, you can still come up with a sharing configuration which is going to be strictly better for both, right? And once we say that there are strictly mutually beneficial configurations, then we are able to also characterize the Pareto frontier of these mutually beneficial sharing configurations. So mathematically, that looks like this. So I plot the loss of load rate for agent 2 on the vertical axis, for agent 1 on the horizontal axis. The blue region can be thought of as the pairs of reliability that are achievable among all possible sharing configurations. Noting that each one of these agents wants to minimize its loss of load rate. The Pareto frontier in this case is the bottom left boundary of this achievable region, right? So that's kind of the efficient region of operation, right? That's the region over which one person's reliability could only improve at the cost of the other, right? And so ideally, you want to operate on that Pareto frontier. Right? So that's basically that's basically what it is that we will do in this piece of work. Right. And finally, once you have a Pareto frontier, well, there is a very well-developed theory in economics corresponding to the theory of bargaining, which one could then invoke to reason about what is the exact agreement point going to be. Okay. So here is the standalone model. I can go through this quite quickly. Our model for each standalone agent is going to be quite similar to what we had before, right? You have generation, you have demand, you have a battery size. Each of these is now indexed by I because you have two agents, right? Agent 1 and agent 2. So the rate of change of the battery level of agent I is basically going to be dictated by the instantaneous net generation of agent I, right? And as before, the net generation of agent I is going to be thought of as basically being some function of a background Markov process xi, right? So each agent has its own background Markov process, right? And so importantly, we're not making any assumptions on the relationship between the background Markov process of agent 1 and agent 2, right? Again, these could have these could be arbitrarily related to one another. And a reliability metric, as I defined before, is going to be the loss of load rate, right? The amount of unmet demand up to time t divided by t, take the limit of that, the almost sure limit of that as t gets to infinity, right? So this is, again, as I said before, very general model. It allows for arbitrary dependencies in between the supply and demand of each agent and also across agents, right? Arbitrary correlations and interdependencies in all of these is captured. RAM constraints are captured as before, and so on. It's a very general model. So here is our sharing mechanism, right? So sharing mechanism is that suppose agent 1 runs a deficit, then agent 2 transfers, if suppose agent 2 has energy in its battery, then it transfers energy to agent 1 in order to meet its deficit, but up to a maximum transfer rate of C2. Okay, so C2 in some sense is an indicator of the extent to which agent 2 is willing to help out agent 1 in times of need, right? Reciprocally, when agent 2 faces deficit and agent 1 has energy in its battery, it transfers energy to agent 1 to meet its deficit up to again a maximum transfer rate of C1. So C1 again is indicative of the extent to which agent 1 is willing to help agent 2 in times of need, right? So this pair C1, C2, where Ci captures the extent to which agent I is willing to share its energy with the other, is basically defining my sharing configuration, right? And because there might be some potential transmission bottleneck anyway, we just assume without loss of generality that this pair C1, C2 lives in some square, right? So each of these parameters is constrained to lie between 0 and some constant C. Okay, so I should note here that an explicit characterization of the loss of load rate is extremely difficult in this model because of the coupling between these two processes. If you were to numerically compute this, you would have to solve a certain partial differential equation with a very messy boundary condition. So this is not something that is easy to compute, or for that matter, come up with any form of closed form characterization form, right? It's a mess. So how then do we say, manage to say something interesting about this rather complicated object? Interestingly, we are able to say something interesting about this model by using sample path techniques. So the sample path techniques will basically let us prove structural sensitivity properties of this model, and in fact reason about the Pareto frontier, even without having like a very clean analytical characterization of the loss of load rate. Okay. So using these sample path properties, here are some of the structural properties that we are able to prove. The first of these says that the loss of load rate of agent 1 is an increasing function of C1. This makes intuitive sense. If agent 1 is willing to share more energy with agent 2, that should hurt the reliability of agent 1. The second statement tells you that similarly, loss of load rate of agent 2 is a decreasing function of C1. Right? So if agent 1 shares more with agent 2, it suffers, whereas agent 2 benefits, right? These are natural monotonicity properties. A third interesting property is that if you look at the sum total of the loss of load rate, right, which if you think of can be thought of as a systemic loss of load rate, right? That is in fact a decreasing function of C1, right? So if any one of these agents is to share more with the other, it suffers, the other guy benefits, and the system on a whole benefits, right? That is kind of what these three results state. And these are all proved basically using the sample path properties that I talked about, right? So the immediate takeaways from this is that from the third statement, it follows that social welfare is maximized at max share, right? It makes sense for everybody to max out their sharing parameters. But the first two statements say that in fact, the only Nash equilibrium between the agents, if I think of Ci as the action of agent I, is going to be 0, 0, right? Because given the other person's action, I have a unilateral incentive to bring my sharing rate down to 0 because that improves my reliability, right? Which is another way of saying really that this non-cooperative framework is in fact meaningless to actually even think about energy sharing in this particular context. So because it disallows the possibility of there being binding contracts between the two agents, which is why you really need the framework of bargaining theory, right? Which allows you to have binding contracts between these entities to get meaningful sharing configurations, right? So with this background and with these monotonicity properties, here is the result that we can prove, right? Firstly, we are able to say that there always exists a mutually beneficial sharing configuration, right? Strictly better for everybody. And the set of Pareto optimal sharing configurations involve at least one of these agents sharing everything, right? At least one of these agents are going to be sharing at the maximum possible rate on the Pareto frontier, right? Pictorially, this looks like this. So the square there is a set of feasible configurations. The Pareto frontier is basically some subset of the red boundary, the upper and the right boundary. In fact, we can say we can be a lot more precise about characterizing this exactly, but given that I seem to be running out of time, let me skip this bit and instead just give you a one-line intuition on why this result holds, right? So consider some interior sharing configuration, which is shown by the black dot out there, right? Then we ask, what are the set of first order perturbations? What are the directions in which I can perturb this particular sharing configuration in a manner that is beneficial to agent one? That gives you a cone of that form that I have indicated here. In particular, note that increasing C2, which is the vertical perturbation, is of course going to be beneficial for agent one, right? Then we ask, well, what is the cone of mutually of beneficial, shall we say, perturbations for agent two, right? That gives you another cone. And what we are able to prove using the monotonicity properties that I flashed in the previous slide is that these two cones will always have an intersection. In other words, there is guaranteed to be at least one direction where you can perturb your sharing configuration in a manner that is actually going to be better for both parties. And once you're able to do this, well, you know that these interior points couldn't possibly be Pareto because you can always make a bunch of these first order perturbations until you get to the boundary, right? So that gives you some sort of intuition about why this result holds, right? And once you know what the Pareto frontier is, and one can actually say more about it than just saying that it's a subset of the outer boundary, you can now invoke the rich theory of bargaining to basically capture the sharing configuration. So you can capture everything from asymmetries and bargaining power, all of this stuff the economies have already done for us. So we just invoke the theory upfront. Right. So we also have a case study in the paper, which I won't get into. Feel free to look at it if you're interested, using basically sharing between one agent, which is basically having a solar generator, another having a wind generator. Obviously, these two have fundamentally different properties, and yet they're able to productively share energy in a manner that is improving the reliability of both. Right. So very quickly, so to summarize, we have talked about the dynamic energy sharing between battery equipped entities in a manner that's mutually beneficial. The main hammer that we have used to capture the Pareto frontier is this idea of using the sample path, right? Study by a coupling of the system, study how the sample path properties change when you increase the sharing parameter by, let's say, some ever so small amount, right? And so this framework is quite powerful, because in particular, it is not very sensitive to the Markov modeling in the first place. Right? It was the sample path property. We do use the Markov model to ensure that, for example, certain renewal cycles are well behaved and they have finite expectations. So for minor technicalities, we use the Markov model, but at a higher level, the Markov model is actually not even required for this. Because we are working with sample path, I could potentially work with battery inefficiencies as well, although that is something that we haven't really managed to do yet. That's something that I'm hoping to do, because again, it's sample path, right? And then finally, I don't even need these long run time averages to work. I could also define reliability over, let's say, a month or a week or an hour. And I can still talk about mutually beneficial configurations at finite timescales, because I only care about the sample path over that particular window of time. So I don't even need these time averages to exist or be well defined, right? And the main, shall we say, to do from our side on this particular problem is to basically generalize this mechanism to more than two agents. Right? How do you go to multi-agent? How do you design the sharing configurations in that case, and so on? Right? So I will stop here to allow some time for questions. Thank you.
Thank you. Thank you, Jayakrishnan. And just as he said, this is, please feel free to ask questions. The way it works in this webinar is that I think Alexis will have to give permission for someone to speak. So if you raise your hand, then she'll notice that and give you permission to speak. That's how it works. So does someone have a question of some kind? You can raise a hand or you can write something in the chat box. Actually, let me kick off and then maybe people can think about their questions. So Jayakrishnan, thank you very much for this very interesting talk, right? There's all kinds of interesting elements in there, which I'd like to follow up on later. But let's just ask this basic question about the time constants in the first part of the work on the Markov chains. I guess the question I have at the back of my mind is Markov chain modeling the right one for a practical scenarios, or is mathematical programming the fluctuations the ones that dominate? Do they need this fine scale Markov chain modeling, or are there other reasons for really using fluid models and non-stochastic approaches. Do you have a comment on that?
I think the motivation is just actually, so the sizing thing is just an application, but I think the kind of subsequent, yeah, I think it's the modeling power that you get out of Markov models that is the primary motivation for us. And there is also a lot of precedent for this. So for example, there is a broad literature that goes back several decades in trying to fit a Markov model on, for example, say a renewable, the data trace from a renewable generator, right? So this is not something that we have done for the first time. People have tried to, for example, come up with hidden Markov models for a given renewable generator trace, come up with Markov models which are as simple as saying that the state is just the present generation, or you look at the state as the current generation and perhaps the generation over the last hour sampled every 5 minutes. So the whole bunch of work that already exists for successfully fitting Markov models to basically renewable generation. So our motivation comes from the fact that there is analytical tractability to be had, and the fact that others and us have been able to actually fit Markov models to real world data traces quite well.
So if you come down to some basic economic measures like size of battery or size of the transmission network and the cost of those things, is the fluctuations at the time scale that you're modeling the dominant one, or is it the fluctuations that happen over seasons or over days or weeks more dominant, right? So
that's a great question. Yeah, of course. So one could in principle construct a very complex model that captures all of the seasons that you might like, but you can imagine that the state space of that could be really enormous, right? Because you can have periodic elements to your state space, which will basically which will act as some sort of a timer, which allows for intra-day variation, inter-day variation. One could do this. The model would be really messy. The way we would approach this is that you use the Markov model to basically think of relatively short-term fluctuations, and you learn a different Markov model, for example, for the summer, and potentially a different Markov model for the winter, and so on, right? In the sense that the Markov, for example, you depending on how the weather changes, for example, you learn a bunch of Markov models over fair horizons of time. And if sizing is your objective, then of course your sizing would be dictated by the large. So, for example, if in some of our work, we have basically found that our Markov fit is much better if we restrict ourselves to, for example, to choosing 3 months of the year, where at least the first and second order properties of the process seem to be fairly matched, right? If I just very crudely segment the process based on first and second order properties and fit separate Markov models for each of those periods, which are I think 2 or 3 months in duration each, that duration is long enough that your stationarity is achieved and your time averages are perfectly meaningful and so on, and yet it's small enough that a relatively compact Markov model can still do a good job in fitting the process over that time, right? So I don't think there's a universal answer to it, but at least the way we have done it and is that you can come up with fairly reasonable Markov models, compact Markov models for moderate time horizons, and you would have several of these, maybe 2 or 3 for a year, for example.
Thank you, Jayakrishnan. There's actually 2 questions. One of them is a technical one from Bert Steart. Alexis, perhaps you could just allow Bert to ask the question in person. I could read it.
We also have another raised hand as well, Bolin Zhu. I'm going to start with that one. So Bolin, I'm going to allow you to talk.
Yep.
Hello?
Yeah.
Okay, now I'm talking. Hi. Yeah, thanks for the great talk. I'm an assistant professor from Earth Environmental Engineering, and I work on electricity market and energy storage, so this is pretty relevant. So actually, I would like to follow up with Professor Mitra's point on Markov models. So one experience I got when applying a Markov MDP to energy storage is it ended up with having problem with efficiency, right? At 92%, 93% efficiency, so it's be very hard to accurately discretize the state of charge segment. And it's the model we eventually run off. So on the other hand, if we improve the granularity of the state space on state of charge, it will increase the entire MDP structure exponentially. The computation complexity exponentially. So what's your take on that, on the scalability versus accuracy over MDP in the storage?
That's a great question. We have experienced exactly that issue ourselves. So the short answer to your question is that in the narrow context of the kind of questions that we are asking, the scalability is not such a problem, because if you think about in the very first model that I described, where we were talking about sizing, the state space is actually continuous. So in fact, the state space is, the continuous set of battery levels. So I don't lose any granularity. And remarkably, even with working with a continuous state space model, you can still come up with, those estimates that I produced, that I presented were in fact for that continuous state space model, right? Similarly, for the case where we talk about economies of scale, I don't particularly care how complicated the Markov model is, right? Because it's basically saying that, a certain economy of scale will show up irrespective of the individual messiness or, the explosion of the state space, but potentially of each of these separate Markov models, right? So for the specific questions that we have been asking in the context of this talk, the Markov modeling is not a problem. However, if you wanted to pose an MDP, for example, if you want to pose the operation or the scheduling of the battery as the optimal solution of a certain Markov decision process, then I fully agree that you would have to deal with this mess. Namely, that you have to discretize the battery levels somehow. And if you discretize very finely, your state space will explode. If you don't, then your answers are going to be extremely coarse. So that is something that I don't have it's not something that is an issue for the work that I described. But if I wanted to pose battery management as an MDP, that's indeed an issue one would have to deal with. And I have not done this yet. I would expect that some sort of function approximation type ideas would have to be applied to make that a bit more tractable.
Yeah, thanks, Jay. Yeah, thanks. A quick question on the another question, if I may.
Yeah.
Is about the gaming, the gaming model in the end for energy storage. So also this is, I think, the problem eventually come to computation, that when we apply gaming model to storage, and the storage has its underlying state of charge constraints with efficiency and upper lower state limits, which make it a kind of a nonlinear dynamic system. And a lot of this game theory model ended up being really computation challenging. We have agent that has internal this kind of constraints. So again, what's your I guess I think you may have mentioned a little bit in the talk, but what's the computation challenge?
So in our particular case, the computational challenge is not hard because we are working with two players. As I mentioned, in the generalization, these are issues we would have to deal with. In the two-player case that we considered, the Pareto frontier is essentially, it can basically be flattened into a one-dimensional curve, right? So ultimately, any computation you want to do, for example, you want to compute the Nash bargaining solution or some other bargaining solution, basically boils down to just doing some sort of a 1D search on a compact interval. So that it turns out to be not so bad for us, but in general, I agree that is a problem.
Okay, thank you. Thank you, Jay. Yeah.
Alexis, I think Bert Sturt has a question. Perhaps you'd like to ask that in person.
Yeah, Bert, I'm going to give you permission to speak as well.
Can you hear me?
Yeah.
My question is there a theoretical limit to how many sources and grids can be coupled together while still being beneficial to all loads using your model?
Are we talking about the energy sharing model or the battery sizing and economies of scale model? Which question is this? Which of the problems is this applied to?
The first of the two.
No, there is no limit. Well, there is a practical limit in that there's only so many locations that one could find, let's say 300 miles apart on the surface of the planet. So there are considerations of those kinds, but from a mathematical standpoint, so far as so long as statistical independence is guaranteed, that statement holds no matter how large n is, right? So the limit would be a practical one, namely that, for example, in the continental US, you would basically have clusters where you have strong correlation, and of course, you have some separation across, right? So given the overall geographical limits that one has, there is going to be certain natural geography induced constraints on how large n will meaningfully be, while still you getting the full benefit as advertised. That's the only constraint.
I'll just add one more point here, which this is Ankur speaking. So one other thing which you need to note is that we've done our calculations for wind energies, and so wind energy has this property that 300 miles is sufficient to give us the kind of economies of scale that we are claiming. The same may not be true for solar energy. So it may be that the sun shines sunshine is more correlated across locations, and you may need farther apart locations, or some other way of ensuring the kind of economies of scale that we are mathematically hoping for also begin to kick in.
Okay, thank you.
Somebody had a question about if this event will be recorded. So we are recording today, and we will publish it on the Data Science Institute YouTube channel. We'll also share it in our weekly newsletter that goes out every Tuesday, and I'm sure Debasis will also email the video around the department. So if you can't find the video, I'm going to leave my email in the chat. Feel free to email me, and I should have it published by early next week, so I can send it to you directly.
So Jayakrishnan, I have a quick question here. So, just from nitty-gritty economics, you can go to the tail of the distribution, overflow distribution for your batteries, so there's the cost of the battery and there's the cost of the transmission lines, or the size, the capacity of the transmission lines. But you can trade that off against some sort of backup generators, right, which be sitting around. Is the trade-off obvious that one way or the other? By having backup, you could reduce the cost of the battery to catch the absolute tail and also reduce the capacity of the transmission line, right?
That's a great question. We don't have a clean answer to that. So you have brought another dimension into the picture, one involving this standby conventional generation, which could kick in and compensate for times when the renewable generation dips. But even, for example, even without that, there is a trade-off involving transmission capacity augmentation and storage and conventional generation being used in general, and the overall penetration here. So at this point, we are only able to ask a very simple question, namely that if so much renewable generation is to be brought online, and the goal is to meet a certain level of reliability, how much can be gained by sharing the battery source? That's the only question that we are so far able to answer. In the broad trade-off space, there are several dimensions, including the one that you mentioned. And so, doing like an extensive case study to figure out what is like the best case, shall we say, resource allocation policy, given all of the time scales involved and so on, I think that would be a very interesting and also a very complicated question.
Right. Any more questions?
I don't see any more questions, and we're actually a little bit over time. But again, I will post the recording on the DSI YouTube channel, and if anyone has any questions for me following the event, feel free to email me, and I can relay the messages back to Debasis and the group.
I have a noisy caller. Okay, so Jayakrishnan, all I can say is this has been wonderful. The talk content was wonderful. It was wonderful actually to stretch the limit and Zoom, and this has made it possible to have somebody from Mumbai talk so well. So Thank you very much. And thank you.
Thank you.
Thank you.